Q times the electric field at that point. So 3.1 times 10 to the negative third coulombs times 954.63 newtons per coulomb I hat minus 875.74 newtons per coulomb J hat. Because it's a positive charge, the force is in the same direction as the electric field. If it had been a negative charge, the force would have been opposite the direction of the electric field, because then minus sign would have flipped everything. And so now we end up with something. I can't remember if I thought it intensely or said it out loud. The 3.1 microcoulombs, or sorry, millicoulombs, not micro, millicoulombs, that is a very large charge, by the way. You can do some serious damage to someone if they came too close to that. Yeah, the Van der Graaf generator, the charge that builds up on that is, I think, microcoulombs. So how do you solve this? What would you factor out?
Or not factor out, but would you, I guess, use
Generally when it's one thing times two things, it's called distribute.
Oh.
If it's 2 and 2, then it's called FOIL.
Foil.
But yeah, the spirit is still there. You could always do that plus 0 and then FOIL. All right, so distribute. And I think there's somebody, I think, who made the hand gesture over here in the peripheral of doing this. So I can make up numbers again.
2.96 newtons. Yeah.
Minus, I got that part covered.
2.71 newtons J hat.
Are we done?
We can be.
Okay. Yes, we can.
Cool.
I guess done without penalty. As some students have demonstrated on tests, you can be done before you even put any marks down. Questions at the moment? Denise?
What's the Q equals C times the electronic field? Is that like, did you factor that out? Did you factor out the first part to get the second part?
What?
The
Did
one
I
above.
get here?
Yeah.
Did I get? I just multiplied both sides by Q.
Okay.
Other questions at the moment? All right. There's one other case that we need to deal with electric field. Then we're going to pick up a topic that is not really part of chapter 18. But there is a piece which I wish they had stuck in, so we're going to put another piece in there dealing with what's known as electric flux. And that, using electric flux, will be able to allow us to find the electric field from distribution of charges and not just always treat everything like a point charge. All right. The electric dipole. So, what is an electric dipole? Based upon gut feeling,
An
the words.
electric field with two poles.
And what would cause an electric field with two poles?
Two of the same charges? Two thingies with charge,
Close, not the same charge,
opposite charge?
opposite charge. So an electric dipole, you'll have a positive and a negative charge with the same magnitude, just opposite signs, that are a set distance apart.
You said they have the same magnitude, right?
Same magnitude. So plus Q and negative Q. Now, how realistic is this, that we have these two charges that are a set distance apart? I mean, why wouldn't they just go collapsing into each other and therefore change that distance? Well, realistically, if you take a water molecule, you have an oxygen here with two hydrogens. Again, they're sharing these electrons right here, leaving the nucleus there, and I've got electrons over here. The distance between the ends here is relatively constant. If I expose this to an electric field, so I take this water molecule and I expose it to an electric field, what's going to happen to the water molecule?
Those electrons.
How will it move? Will it rotate clockwise, counterclockwise, just translational, move away, move towards, up, down, in, out? Well, just give you some encouragement, yes, it will move. It'll move this way. It will move like that.
No, other,
Yeah.
It'll move like that.
yeah. So where the oxygen is that way and the hydrogens are that way. No, because the hydrogens are positive. It's going to do the opposite of what I just said.
Right. Yeah.
But is that your final answer?
No, it's going to do what I said.
All right, so
That's my final
at least one of your answers is correct. So, someone else want to chime in and help Sarah out?
It's the opposite.
I say it's
The
good that way.
oxygen goes
It's
that
good.
way,
It's not.
the hydrogen goes that way.
Why would it
But
do
they
that?
don't move apart. It's just like the way it rotates.
But I thought the opposites repel, so it would make sense for the hydrogen because they have a positive charge for them to go towards the electric field more than. I mean, they're going to be moving together.
But in the works, it says that if Q is less than 0, which means Q is negative, then it's going to go downstream. That's going to go with the flow.
Yeah.
So what other people have notes? If Q is negative,
It flows towards.
it goes upstream. If Q is positive, it goes downstream. That's what Carly wrote down.
That's what I have wrote down.
Okay. That's a rather critical distinction.
Yeah. What is this supposed to say?
Q is positive, it goes down the stream.
Yeah. So it's going to rotate this way. The negative side is going to go towards the source. The positive side is running away.
Write it down.
I got that. I got it like, it says, I was trying to go downstream.
I'm glad that got cleared up.
Yeah.
Just like over here, the force that was acting on, if I put a positive charge here, the force on it was in the direction of which that electric field was. So positive goes in the same direction as the electric field, negative goes opposite. Now, when this water molecule rotates, and it's possible that it'll just end up oscillating back and forth, but it'll have a sort of a net result of, I've got my oxygen here with its electron sitting there. I have a hydrogen here, I have a hydrogen here with its positive side. What can you tell me about the electric field from the water molecule.
It's gotta be going,
So the electric field, the water molecule is going to create an electric field going that way? That,
Oh.
you said, Joe?
Oh, you mean the
We have this external electric field, but
Okay.
it's a dipole, so it has its own electric field. Which way is the electric field going? Because of the water molecule.
going from the hydrogen to the oxygen.
Yeah, because it goes from positive to negative. And so we'll have a secondary electric field in this direction. It's smaller than this external one, but we have a secondary one. So we end up with this external electric field going sort of to the left and down, and this smaller internal one going up and to the right. So what is the net electric field here compared to here?
Smaller going that way.
Yes. So what a dipole has a habit of doing is it causes the electric field to go down locally. This will have an incredibly huge impact when we get to capacitors. Questions? All right. Now I want to introduce this idea of the electric flux. So imagine I have arrows shooting from that wall to that wall. The analogy obviously would be electric field lines, which are generally represented by arrows. So I have arrows going from my right to my left. And I stick a piece of paper in the way. What's going to happen?
They're gonna go around the piece of paper.
Why would they not go through the piece of paper?
They're gonna go through the piece of paper.
And around the paper?
No, just through.
Okay. They do. I'm curious about their first answer still.
I just figured maybe they wouldn't be able to go through the piece of paper.
No, yeah, like most arrows in paper, arrow can penetrate. All right, so the arrows can go through. Now, suppose I put this like that.
It will still go.
Just still go through.
How? I'm doing a Robin Hood splitting the arrow kind of thing?
Yeah.
Mm.
All right, so will I have more arrows going through it like this or like this?
Like that.
Like that, okay. What about here?
Less.
I say the same.
Less than that, okay. But more than that? All right. So this is the whole concept behind electric flux. It's, I have an electric field going through a surface, and I want to know sort of some idea of how many of those arrows can actually go through that surface. And so the number of arrows depends upon the electric field. That tells you how many arrows there are, and it depends upon the surface itself. However, the angle makes a difference here, because obviously when it was like this, I had more arrows going through it than when it was flat like this. So the angle makes a difference. And so how do you take angles into account? A dot product. It's back. Now, for those of you who've forgotten, or for those of you who did not see what a dot product is, let's sort of do a refresher there. There are two ways of multiplying vectors. One is called a dot product, and the other is called a cross product. So multiplying vectors. A dot B or A cross B. Now, for those who do remember, what is the big difference between, what are some of the differences between dot products and cross products?
Cross products is for when they are perpendicular.
Okay, so this cares about perpendicular. And dot products would be the other. So dot products are multiplying parallel components. And this, let's see, multiply parallel components, and this multiplies perpendicular components. What's another difference between the two? When did we see dot products in the first semester course? Or when did we see cross products in the first semester course?
Dot products were projectile motion.
Oh, in one of the cake formulas?
Mm-hmm.
Okay, I guess that was the first place. We didn't do much with that dot product at that point, other than notation. What was the first place we actually cared about the fact that, paid attention to the fact that it was a dot product? Say it again?
No, I think when we did, the right hand rule, that was cross product.
No, yes. When we do right hand rule?
Rotational.
Yeah, and more specifically torque. So we did cross products when we were dealing with torque. Or more generally, rotational motion cross product shows up a lot. At all. But dot products, when did that show up more rigorously?
That was like magnitude.
Keep going.
It's like A times B divided by.
Multiplying magnitude?
All right, I mean, from a multiplication point of view, it would be the magnitude of A times the magnitude of B times the cosine of the angle between them. But that goes back to when did we see it? Apparently it made a huge impact on your lives.
I don't remember when it showed up, just that it was there.
I'm gonna have to talk to your first semester teachers. Work was forced times displacement. Dot product, we came up with work. All right, so what is a significant mathematical difference between work and torque?
Oh.
Work is linear.
And torque is,
Well, isn't torque?
oh, okay, that's where you're going. You can also have rotational work. We just didn't do anything with it. Yeah, it would be, work is torque dot delta theta. Which does highlight a difference between work and torque.
Yeah.
It's the form.
They're inverses.
She took a.
No.
Is it angle and
Oh.
position?
Say it again?
Angle and position?
Angle and position, no, not in the way I think you meant. Do you want to reword that?
Isn't torque inertia? The angular.
If only there was some way of writing stuff down to give information. Some notation that would indicate what we're working with.
Do you want to know the formula for torque?
Say it again?
Do you want to know the formula for torque or no?
Not necessary for what I'm trying to get across right now.
Is one scalar?
Tina, say that again.
One of them scalar.
work is scalar. Torque is a vector. Dot products produce scalars. Cross products produce vectors. Or for the purists in the group, axial vectors or pseudovectors. This is going to produce a scalar. Now, obviously, physicists don't like writing out the word electric flux a whole lot, so they need a shorthand notation. So what they use is a capital phi with a subscript E. So it's not confused with magnetic flux.